Let's talk some more about those conjugate pairs, okay? Bronsted-Lowry acids and bases, because the whole definition for Bronsted-Lowry is that it's about a transfer between things of a what? Hydrogen ion, an H+, or what we call a proton, okay? And so when we talk about these conjugate pairs, right, we're talking about a species, or we're talking about two species, right? Two things that are only different from each other by just one H+ in its formula, right? Okay. And which species is going to be the one we define as the acid of the pair? The acid is the one that can do what? Can give away an H+. The base is the one that can accept. Okay. So we will become more familiar with what the pairs look like as we go through this chapter. But we should be able to kind of, just with that knowledge, look at a species and write its conjugate, one way or the other. So I'm looking at example before now on our new in class, yeah? Oh, yes. Okay, let's write the conjugate species for each in these little following sets that I have. So here's 3. And I went ahead and told you, okay, these 3 that we're looking at first are acids. Okay, so I'm already telling you they are defined as the acid. So what is the thing that we're going to be writing? It's conjugate base, right? Because that's how the pair works. It's acid and a base are a pair. So if this is an acid, what would I do to this species formula, to HCl, to turn it into a base? The acid is going to do what? Give away. What is it giving away? The H+ in the formula. So if this is the acid species, what is the conjugate base of this acid? Cl minus. It is the chloride ion. It is not chlorine gas, right? It is not chlorine element. It is the chloride ion. Yes. So sometimes when we write pairs, right, we'll write the two species and we'll just put like a slash in between them. Okay, that's the pair. We talked about this one yesterday. What is this acid? This is my favorite acid. So vinegar is the name of the solution that this makes with water. What is this acid name? Acetic acid. Yes, acetic acid is my favorite. And this has some options about which H it's going to get given away. But I told y'all, until we get more into some structure things, which H is it that's getting donated? Yeah, we're giving away that first H listed. Okay. So what does that leave behind? What's the conjugate base? C2, H3, O2 minus. When that neutral compound loses an H+, the resulting conjugate is negatively charged now. Yeah, that's the polyatomic anion known as the acetate ion. Okay. What about this? What is the name of this compound? H2SO4. Okay. I'm telling you it's an acid. You should also recognize it as an acid because it's one of the 6 strong acids you should know. This is known as sulfuric acid. Okay. What's its conjugate? We can only take one H+ away at a time to make a pair. So if I just take one away, I still have one in the conjugate formula. What's here? It started off neutral. I lost one H plus. The resulting conjugate is negatively charged. What's the name of this? This is a polyatomic ion. It has a name. Hydrogen sulfate. An older name for this is the bisulfate ion. Sometimes it's called that. But hydrogen sulfate is easy to remember. Okay, good. What about if I'm going the other way? What if I have what if I have a base? Okay, I'm telling you, here's a base compound. Tell me what the conjugate acid would be of these bases. Wait a minute, did I do that the right way? Oh, I have it written backwards on yours, on your sheet. Okay, well, let me write it the way I wrote it on here then. Hang on, sorry. Okay, so if I'm telling you here's a base, how do you know, how do we define something as a base? What does it mean in this definition to be a base? It's something, any species that can accept an H plus is a base. Anything that can accept an H plus is a base in this definition. Okay. So I gave you these bases. Tell me what would be the conjugate acid species for these. So this has a negative sign. Guys, it can accept an H plus for sure. Okay. What's the name of HNO2? You know that one? So close. This is not nitric acid. This is nitrous acid. Nitric acid is NO3. It's based on the nitrate ion. That's NO3. Okay. So this is nitrous acid with the nitrite ion, and that's a pair. That's a pair. We looked at this compound yesterday, didn't we? What is this name of this compound? Ammonia with benzo with the A, NH3. And part of what I'm teaching you in this class is that this compound is a base. Ammonia is a base. Because it's a base, that means it can do what? It can accept an H plus. There we go. Are you doing acids and bases too? Big old acid base party up in here. Okay. Yeah. Oh. What is the conjugate acid of this base? NH4 plus. And that is the ammonium ion. Good. We looked at this. If I think of water as acting as a base, which we saw yesterday, it can. Water can also act as an acid. It's unusual in that way. I'm going to talk more about that here in a minute. But if I'm telling you, okay, water is a base in this context, water's basic in this context. What is water doing then? It is accepting. And so what is the formula for the conjugate acid of water? This is what water turns into when it accepts an H plus. And what is the name of this thing? This is the hydronium ion. Yes, very important. We're going to talk a whole lot about hydronium ion today. Look at 5. Look at these pairings that I have proposed on number 5. Tell me, are these conjugate pairs or not? And if you say, no, it's not, can you give me a reason why it's not? Let's look at these. I'll talk about names also, because right, this Got to remember our names of things. Let's look at this first pairing. HNO3 and then NO3 minus. Is that a conjugate pair? Why? These two formulas are only different by one single H plus. This is nitric acid, and this is the yes, but I'm talking about name. What's the name? This is the nitrate ion. Nitric acid, nitrate ion. Okay. What about this pair? Why are they not conjugates? These two formulas differ by 2 hydrogens. Does that not mean at some point these are kind of related to each other? I mean, yeah, but in a series. These two directly are not conjugate pairs. They differ by 2 hydrogens. What is the name of this H2CO3 compound? Excellent. Carbonic acid. This is what's in my soda that I drink every day. Oof, bad. So bad. And carbonic acid actually does not like to exist at all. No, it does not. It's very unstable. It prefers to decompose into carbon dioxide, which is the bubbles. It splits into carbon dioxide and water very readily. Okay, so if that's carbonic acid, then what is this compound? Sorry, this is not a compound. This is a polyatomic ion. But what is its name? Carbonate ion. Okay, here's a pair, HCl and the ClO4 minus ion. Are those conjugates or not? Why, Hien, do you think yes? Wait a minute. Why, Hien? You said yes. Is it because this one has a hydrogen and this one doesn't? But look at this compound. This has just chlorine, and this has chlorine and oxygen, right? They are not identical except for the hydrogen. They have other differences. Not a conjugate pair. Okay. What is the name of HCl? Hydrochloric acid. What is the name of this ion? HClO4 minus. That is the perchlorate ion. Y'all may want to refer back to, what was it on the last chapter study sheet, the chapter 15, I think, where I gave you guys the list of all the polyatomic ions as well. That can be helpful to refer back to in the acid chapter. Okay. All right, what about these two? SO42 minus and SO32 minus. Are those conjugates? No, they don't differ by an H plus, do they? They differ by the number of oxygens, but that's it. So that's not conjugate pairs. Sulfate ion and then the sulfite ion. Okay, now what about these two? I really wanted to show these two in particular. Does that look like any compound we've seen? No. Okay, and that's because this is an organic molecule. Okay, we haven't learned about those yet. Do you guys agree that you see carbons, hydrogens, and nitrogens? Yes? Okay. Do you agree that these two are the same formula, except they just differ by 1 H plus? So are these conjugate pairs? Absolutely. I want to make this helpful statement to you guys. Oops. Hang on. Come back. Okay. In this class, in this chapter, a lot of times the weak bases that we'll use in examples are not just ammonia, but often they're like organic compounds that are derivatives of ammonia. Okay, so here's what I want you to be on the lookout for. Something is a weak base if it's a covalent compound with a nitrogen atom. It's very, very likely a weak base. And then I can't think where I would try to And I can't think where you would see when it's not. So this is your rule to look for. How do I know if it's a weak base if I don't recognize the compound? I'm telling you right here. If it is a covalent, so no metals, right? Covalent compound with a nitrogen, it's a weak base. Weak base meaning it's going to do what? Base is going to accept an H plus from something else. So just looking at E. So this is actually what I just showed. It's just the N is written at the end of this formula. Which one of these is the acid and which one of these is the base? Where is number 5? Yeah, how do you know if you're looking at a pair already given, which one is the acid and which one is the base? Well, again, the base is the one between the two formulas that can take a proton, and the acid is the one that has a proton that it can give. This is the conjugate base, and this is the conjugate acid. Right? That's the pairing. Okay. All right. Okay, I don't really know about that just yet. Okay. So let's talk some more about water. Water is what is known as an amphoteric species. Amphoteric means it can behave as an acid or a base. Depending on what it's paired up with. So we have seen that water, if water is acting as an acid, okay, let's say water is going to be an acid in whatever we're looking at, meaning water is going to do what? Give an H plus away. What does that mean the conjugate base of water is? What does it form when it gives an H plus away? OH minus. The hydroxide ion. If water is acting as a base, meaning it's willing to accept, what is the conjugate acid that water forms? H3O plus, the hydronium ion, right? What are some other things that can do this, act as an acid or a base? Well, pretty much anything that is, let me see if I have this other word in here, or if I just want to stick with the word amphoteric. So hang on a second. So it's not every neutral compound. So this is what I'm trying to say. So sometimes there's another word that's used, but I don't know if I really want to use this word. In fact, okay, I think I don't. Let's just stick with amphoteric. Okay. Look, if we're talking about things that are amphoteric, it's anything that can either accept an H plus or it could donate an H plus. So typically we typically see that with these known conjugates of acids. Here are some very common examples of, these are all ions that can be amphoteric. Let's look at just a couple. Let's think about how does that work, right? So, for example, if I have, now you guys got to know, what is the name of this ion? HCO3. Oh, well, it's on the screen. What's the name of this ion? HCO3 minus. Okay, that's the bicarbonate ion. Guys, we know that. Where did we find that? Sodium bicarbonate. This is baking soda, right? It's bicarbonate ion with sodium ions. Okay, soda. This bicarbonate is amphoteric. What does that mean? This can either accept or give away. If this is accepting, that means it's acting as a what? Base. If I tell you, let's say this is going to accept, that's a base. If it accepts, what is the conjugate acid it forms? It forms that carbonic acid, doesn't it? Doesn't it? Okay. If this is going to act as an acid, meaning this species is going to give away an H+, what is the conjugate base that it forms? CO3 2 minus. It was already -1. It gave away its H+, now it's plus. Sorry, now it's -2.
So we need to know that all those are.
I would know that all those are amphoteric, yeah.
Okay. So there's nothing that indicates that we just need to know.
So the indication, here, let's say this. The indication is pick another one of those up there. I don't care which one. Pick another one. Any one besides the one I just did. Pick any of them. Just give me one. Dihydrogen phosphate. Dihydrogen phosphate. What's the charge of that? Okay, -1. Okay, so here's this polyatomic ion. Okay. It's negative charge. Means it can likely take an H+. It can get an H+ added to it. What does that form? If it accepts an H+, what do we end up with? H3PO4, which is a neutral compound. This is an acid. Do you know the name of this acid? You should recognize it now for this class. Absolutely. This is phosphoric acid. Okay. I'll just write these others out just so you can see. Do you see how this not only can take, it has 2 H+ that it could, so it can lose one, and then could we lose then even another one? Sure could. Nope, not 3 minutes. Sorry. There we go. Okay. Okay. This H2PO4 minus, right? When it gained, it formed this acid, right? When this HCO3 minus, when it gained, it formed an acid, right? These two particular acids, these two acids, there's others that do this, but these two acids are what are known as, so this is the word I wasn't going to use, but I guess I'm going to use it now, okay? Polyprotic acids. What do you think that word means? Polyprotic. What does poly mean? Multiple. Protic for acid chemistry means H's, right? Polyprotic acids are acids that have multiple H's. Okay? And what did we just observe about the conjugate base of a polyprotic acid? this conjugate of the polyprotic acid is itself amphoteric. The conjugate base of a polyprotic acid is amphoteric. Meaning this species can do what? It can accept being a base and go back to the polyprotic acid, or it can act as an acid itself and give away another H plus, right? Okay, look here. Is that true? Does that statement I said, is that true? Let's look. Here is a conjugate base of a polyprotic acid, yeah? Can this H2PO4 minus, can this act as an acid and give away another hydrogen? Sure can. Can this act as a base and accept a hydrogen to turn back that way? That's the definition of being what? Amphoteric. That's the definition of it. So while I give you those four that you can know, are those the only four besides water? Absolutely not. What's the better thing to remember if you're really trying to remember something? The conjugate base of a polyprotic acid is amphoteric because it can accept and give away. What about that? Can this accept and turn this way? Can this donate and turn this way? So is that amphoteric as well? But what about the PO43 minus? It can accept, right? It can act as a base. It cannot act as an acid. It doesn't have an H plus to give away, does it? So at some point you can't do both. But these ones in the middle, when you have polyprotic acids, absolutely are amphoteric. Does that help a little bit? Okay. All right. So talking about amphoteric, talking about water. And all of our acid-base chemistry we're looking at is water-based. Okay. Is this actually the next section or is this still this section? This is still this section. Water, because it is amphoteric, does something very unique. And I mean just water alone. Water by itself, not water with anything. Pure liquid water does something super unique. This thing called auto-ionization. Auto-ionization of water. Water molecules have their own equilibrium going on all the time. Water molecules have an equilibrium going on all the time. There is a reaction happening between water molecules all the time. Two water molecules next to each other undergo a little acid-base reaction. Acid-base in our context here. Acid-base reaction, meaning transfer of a what? An H plus, a proton. So one water is going to give, and one is going to receive. A water molecule that gives away an H plus becomes what? OH minus, the hydroxide ion. Is that ion a pure liquid? No, that ion is an ion dissolved in water. It is aqueous. Water is a liquid. Its conjugates are aqueous. They're ions dissolved in the water. What else do I form? Water accepts. It forms what? Hydronium ion, H3O plus. Okay, yes, guys, this is happening all the time in water. But not to a high degree, not to a high percentage. Okay, it's actually very small. What's the thing that we use to judge how much this reaction is going this way or this way? What's the letter that we use to judge these things? K values, equilibrium values. It's the same K. It's the equilibrium constant K, except we're talking specifically about water. KW, K water, KW. This is known as the ion product constant for water. You tell me in a K expression for this written, let me give you all a second. In our K expression, writing the K expression, products over reactants, right? What does my K expression for water ionization, auto-ionization look like? Product, right? Reactant.
No.
Why not these two water molecules? Because they're a pure substance. They're pure liquid, no concentrations. So KW for water just looks like what? Products, ion products. That's why this is called this. Ion times each other. Will the KW of water always look like this? Uh-huh. Uh-huh. Does it matter which one of these ions you write first? No. It's hydroxide times hydronium. That's it. Now, this wouldn't be a constant if there was not a constant value, right? For water. And like all K values, at all K values, it is dependent on what? The only thing it's really dependent on to be constant is the temperature. So this value specifically is when water is at 25 degrees C. If you go to higher or lower temperatures, this can be a different value. We will not be worrying about that, okay? 25 degrees C is what? Room temperature. That's what in science we call room temperature. That's about 76, 77-ish degrees Fahrenheit, which is too hot to be room temperature, right? Amen. But 1.0 times 10 to the negative 14th is the value of KW at 25 degrees Celsius. Which means the concentration of hydronium times the concentration of hydroxide. Not times, excuse me. I already said that. What does that mean? These two numbers multiplied always equal this value, right? Constant. What does that mean? These two concentrations equal. Give me the equilibrium value of each of those ions. How would you solve that? Square root of KW, right? X times X. Take the square root. What's the square root? This to the 1/2, right? This to the 1/2. And negative 14 times 1/2 is negative 7. This is the concentration. This is the molarity of each one of these. Because of math. No, not conjugates, because of the math. Look at, let's pretend I wrote an ice table. Let's pretend I wrote an ice table. 0 initial. These are products, so they are plus X. What's the ratio? 1 to 1. So plus X, plus X. So at equilibrium, X and X. Okay. X times X. X squared, right? Okay. Okay. This concentration, let's write this down, is the concentrations when the solution is neutral. Y'all know this term neutral? We're talking about neutral in a pH sense, neutral in an acid-base sense. If I tell you a solution is neutral, now, automatically, if I tell you it's a neutral solution, what does that mean? The concentration of hydronium ion is 1 times 10 to the negative 7th. If I tell you it's neutral, what does that mean the hydroxide ion concentration is? Yes. True fact all the time? Yes. True. When does it become acidic or basic? When these aren't equal anymore. That's when we become acidic or basic, when these are not equal anymore. So that's our next section. Do you want to go ahead and take a break, or do you want to start this section and then you start this section and then take a little break? Let's do that. Oh, okay, here. I do have two quick practices that we can do. So I just did this one. This is number 6 on our in-class example. What are the concentrations in pure water? That was this. The concentrations in pure water are 1 times 10 to the negative 7th for each one. Okay. And pure water is what we know to be a neutral solution, right? It's neutral. Okay. But what about this one? What about number 7? Okay. So I've got an acid in water. So I just want you to be thinking. We know if I put an acid into water, what is that ionization equation looking like for that acid? Just think. That's not what this question is saying, but just think. What is that reaction between acid and water look like? So, hey, Loretta, remember what does this mean if I write WA?
With acid.
Weak acid. Okay. So another way that we will talk about a weak acid, just very generically, and this is used all the time. So just, okay. HA. That means I don't need to know what this ion is. It's just some ion, okay? But this acid is going to be a weak acid, whatever it is. Just think, if I react a weak acid with water, this is a, what kind of equation am I writing here? I tend to default to the word ionization equation, but what was another word we could use? Dissociation, right? Okay, but I tend to say ionization. Think. What is happening here? It's in equilibrium because it's weak. What does the weak acid do? What do all acids do? They donate, right? Okay. So what does that leave behind. What's the conjugate base of this weak acid HA? A minus. A minus. A minus. That's aqueous, right? My weak acid is also aqueous. It's dissolved in water, right? Water is the liquid. What does water form? Hydronium ion. So now this problem, number 7, I'm saying that in this problem, I have put a weak acid into water, and I figure out that the hydronium ion concentration is what? 2.0 times 10 to the negative 6 molar. Guys, is that 1.0 times 10 to the negative 7th? No. Obviously, it's not. It's 2 different numbers. If this is the hydronium concentration, what is the hydroxide ion concentration in this solution? And then you're like, there is no hydroxide, Miss Poe, that's an acid. No. Why is there hydroxide there? Why is there always hydronium and hydroxide? Because water is doing its own thing the whole time. Water is doing its own auto-ionization the whole time this is also going on. You always have, oh, I say always, you should always have some of each of these. Okay. But what's their relationship? When you multiply these two together in a water-based solution, they ought to always equal what number? KW. They have to equal KW. They have to. That's the constant part of it. So, do you know KW always? Yes. What is KW? 1 times 10 to the negative 14 equals your hydronium times your hydroxide. Always. Solve for hydroxide.
So you're not worried about the A?
That's not what this question asked about.
Or would you do the same thing if it did?
If I told you the concentration of A, could you do something with that information? Yes. Could you take information about A and get information about OH minus? Not really. Good. You have to do several steps. Why can I use hydronium to figure out OH minus and not something else? Because of this relationship is established and known. I don't have a relationship, as you know right now, between this and OH minus yet. I do have a relationship between hydronium ions and hydroxide ions. So what's the OH minus? 5.0 times 10 to the negative 9. Molar. It's a concentration, right? Molar. Big M. Moles per liter M. That's how we don't say it. It's that's we say molar. That's the way. That's the English of it. That's the way we say it, right? It's the verb. It's the correct tense, right?
I want to know. I'm not taking English class right now.
This is chemistry English class. So is this solution acidic or basic? You guys are saying it's acidic. Why?
There's more hydronium.
Okay, so this is the math answer. This is what I want us to learn about. But just in general, maybe you could just read the problem and say, well, you dissolved an acid in this solution, so I bet it's an acidic solution, Ms. Poe. Yes. But the math answer, the real way to think about it is when you have a neutral solution, what is true about the concentrations of these two ions that are always there? They're equal to each other. What is true if you have an acidic solution? And how are they not equal? What is the imbalance, Laura? Tell me which one is there more of? Do you suspect? Which one did I tell you is the acid thing? Hydronium ion is your acid species in water. If a solution is acidic, there is more hydronium than hydroxide. And then if the solution is basic, or another word that we use, actually, the word that's really preferred is alkaline, but basic is fine as well. What is the imbalance? You have more hydroxide concentration. Okay.
This is getting into section 14.2.
Yep, this is where we're about to start. Yep. So in this number 7, here was the hydronium ion, 2 times 10 to the negative 6. Here was the hydroxide, 5 times 10 to the negative 9th. Compare the two concentrations, and that'll tell you which designation it is, neutral, acidic, or basic. And it's, Joseph, what did we say? This is much bigger than this number, right? So it is acidic. We don't like to do normal people, so not scientists, not chemists. Normal people don't like to deal with numbers and scientific notation, and they sure don't know about molarity. So we have a different way to talk about acidic, basic, neutral, which is the pH scale. So that's what we're going to pick up with when let's take a break and then we'll come back and we'll look at that. And I'll say that's where we're going to officially start section 2. Okay, is with the pH scale. And then
Is this thing we're going to be working with the pH strips in lab?
we will work with pH strips in lab. Take a little break.
Big one.